All right, ladies and gentlemen, today we're going to be talking about the Nernst equation. So we're still in equilibrium. We have the Nernst equation. So we have our delta G is equal, this is the Gibbs free energy equation, delta G equals the delta G naught plus RT ln Q. We're going to use that equation to find the EMF at different conditions, the electromotive force that we talked about before. So we have our electromotive force, our reduction potential is equal to the standard reduction potential minus the quantity of 2.303 times R times T divided by N times F, all multiplied by the log of Q. Might be asking, what are those variables? All right, R is equal to, it's our gas constant of 8.314 joules per mole Kelvin. You guys have seen that before. F is our Faraday's constant. You guys have seen that too. So it's 96,500 joules per mole volt. Our N in this case is going to be our number of electrons in the equation, the half reactions. And our Q is going to be our concentrations of reactants and products. Now we can have this equation at standard conditions. We can simplify things a little bit if we're at standard conditions. So the general equation right here, this guy is for different equations or different conditions that are not standard. We have a separate equation for standard conditions. We can solve for T, R, and F because we know all of those. We can plug those in. We have our E is equal to E naught minus 0.0592 volts over N still, because we don't know the number of electrons in the equation, times our log of Q. That's because our standard temperature for voltaic cells is 298 Kelvin or 25 degrees Celsius. So when we plug that value in, we plug R in, and we plug our gas constant R and Faraday's constant F into the equation. We can simplify that a little bit if you're at standard conditions. Don't use this guy for different conditions. For different conditions, we're going to use this one. All right. So do an example here. We have our equation here. Bromine Br2 plus lithium goes to lithium ion plus 2 Br minus ions. So we have to find the electromotive force for the above reaction at 28.5 degrees Celsius if the concentration of bromine ion is 0.3355 molar and the concentration of lithium ion is 0.5555 molar. Now we see in our equation, we have a temperature that is not our standard temperature, so we have to use our non-standard equation. First we have to do is break up our equation into half reactions. So we have our Br2 goes to Br minus. We have to balance those up. So we have 2 Br minus. We have to balance the charges. So we have to add 2 electrons to our reactants. Our other half reaction, lithium to lithium ion. So it's a cation. So lithiums are balanced, but our charges are not. So we have to add an electron to the right side. Now, remember, we have to find a common multiple for our electrons. So we have to multiply our lithium half reaction by 2 to get 2 electrons. So we have a balanced equation there. We're going to pull up your table that we're going to post on Google Classroom so you guys don't have to lug the textbook around. Our standard reduction potential for the bromine reaction is 1.09 volts. Our standard reduction potential for the lithium half reaction is negative 3.04 volts. Remember, this number, we don't multiply even though we multiplied the half reaction by 2. We keep this negative 3.0 volts straight from the table. No multiplication for that part. All right, so we have our standard reduction potential is equal to the cathode minus the anode. So we have 1.09 volts minus a negative 3.04 volts. Turns into an addition problem, and it's 4.13 volts. We plug that into our equation here because we're not at standard temperature. So we're not at standard temperature, so we have to use this equation where we don't have it simplified for you. So we plug in all that we have. So our standard reduction potential at 4.13 volts minus, we get that 2.303 times our gas constant times our temperature. We convert that into Kelvin from 28.5 degrees Celsius. So we add 273. That's all going to be over the number of electrons. That's why we multiplied our half reaction here by 2, because we have 2 electrons for our bromine reaction. So we have to have 2 electrons for our lithium reaction. So the number of electrons is 2 times Faraday's constant. all that is times the log of Q, which is our concentration of reactants and products. So we have to balance those up. So we have our 2 lithium ions here, our 2 bromine ions there. So it's our ion concentration. So we have 0.5555. Because we multiplied by 2, we have that, we're raising it to the second power for both of those. And then 0.3355 for our bromine ions, again, raised to 2. Solve for that, we get minus a negative, so plus. We get our final answer of 4.17 volts. All right, we'll do this one together in class. So cadmium solid plus 2 silver ions aqueous goes to 2 silver solid plus cadmium 2 plus aqueous. Remember, when we're doing these with our solids, we don't count those for concentrations because solids and liquids don't count. Gases and solutions are the only ones that we're counting for our concentration. So calculate the EMF at standard conditions if the concentration of cadmium ions is 0.3545 molar. The concentration of silver ions is 0.7899 molar. Like I said, we'll do that one together in class. I'll have you guys work on this one. So find the EMF of the copper zinc reaction where the concentration of zinc ions is 0.2555 molar. And the concentration of copper ions is 0.3955 molar at 46.8 degrees Celsius. That's all we have for today. We'll see you in class. Take care.